Hello YouTube viewers, welcome to my show Future Friday. In today's episode, we're going to talk about a true starship, basically a spacefaring system that we need for Earth and Mars transport. So first we have to understand space is ludicrously hard. We have no inherent understanding of it first because most of us never left Earth. So that is the first thing. Second, long-term stay in 0G is very deadly. Now many people will say, oh, it's not 0G, it's low G. Yeah, I get it, it's tomato simply because once you are inside a spacecraft, inside ISS or something like that, you are experiencing 0G. You can have a gravity meter and be like, yeah, it's zero. You can put a pen in there, it will keep floating. It's not micro G. Micro G will be on moon basically, where it will drop. Again, it will drop slowly, but it will drop. So 0G, while you are transitioning there, yes, you are inside basically sun's gravitational world, but you will not have like, oh, if I left this pen here, it will fall into the direction of sun. That will not happen. So yes, you are in quote unquote 0G, and that is flat out deadly. We have no idea what happens to you when you are in low G environment, basically like moon or Mars, but we know for a fact, for an absolute certainty, that 0G is gonna destroy you, flat out destroy you over time. Again, it's cumulative, basically it's like radiation poisoning. It will not do, oh, you are exposed to it, you're dead. Like if you are exposed to it long enough, yeah, you're definitely dead. So 0G is like that. First it will start to erode away your bone, your muscles, your kidney will be overwhelmed because of so much calcium it has to remove. Other things will happen, and not to mention you have lovely radiation to make sure that you are thoroughly roasted. So you have a lot, like we understand that, like we need gravity, otherwise like our immune system breaks down. So we need that. It has its own unique challenges, simply because if you are thinking about living on moon surface, it's one kind of scenarios you have. You are thinking about living on basically Mars surface, it's something else you have to think about. But when you're talking about space, it's something independent. It's not something that you like a design that is well suited for space will not be well suited for basically Mars or moon. So it has its own unique challenges, and one ship cannot do it all flat out. Like, can you make a BFR that takes off from Earth, goes to Mars, land there, refuels it there, and then come back? Yes, absolutely. Would this be pleasant for the astronauts that are inside? Flat out no. Most of them will be literally in a very crippled state when they reach there, because best case scenario is 4 months in 0G. Not a good experience. So flat out, space is hard and we need gravity. But space does have some kindness to herself, and there is some serious advantage that we have. Mass, basically how heavy your craft is. Basically ISS is 600 tons. It goes up and down because not only experiments are added and removed, you also have crafts that are added and removed. So mass goes up and down, but average I always say is like 400 to 600 tons. So mass is very manageable, so you can make it as big as you want. Like if you want to make, let's say, for you are like, okay, this craft will be there doing ferrying back and forth, and if it's only designed for let's say space environment, it can survive for a very long time. Heck, ISS, it was not even built for this kind of lifespan. It's already working for 30 years. So you can design a craft that can last in space for very long time. So, and not to mention, you don't have weight constraint that you will have if you have to design something that lands or takes off. You do not have weight constraint. So space is a kind in that kind of scenario. Aerodynamic is not an issue. Again, space, vacuum, absolutely vacuum. But again, ISS has to worry about aerodynamics. It worries about it so much that every time it goes into the shadow, the solar panel are aligned to the orbital plane. Basically, if your orbit is like this, let's say this is equator, your orbit is like this. Again, orbit is generally like this, but let's say it's like this, your solar panel will be aligned to this. So you have less drag, because they have to keep reboosting this puppy every few years. Not even few years, I think yearly nowadays they are doing. So aerodynamics, that means you can have weird designs and all that jazz. Top speed will be the same. Now here's the deal, this is very interesting. You did increase mass, and inertia, physics and all that, they remain the same. So the only side effect you have to deal with, if you made it ludicrously heavy, acceleration time would be very severely. If your rocket is the same size, your acceleration time would be much longer. Let's say if 600 ton was like, let's say it took 1 week to accelerate using ion engine. If it's 6,000 ton, it will take 6 months to accelerate. So you cannot go YOLO unless you have YOLO kind of power supply and rocket thrusters. So space is kind in certain regard. You can have like ludicrously heavy crafts on that. Now this BFR concept, while it's very good and it does get us Mars in a hurry, it's not a long-term solution. simply because long term stay is completely different. If you have to put like you were saying like the inside space is bigger than ISS. Here's the deal: ISS people already classify it as a cramped space. Imagine that kind of volume, livable volume you have, and you want to cram 100 people in it. Again, we do that in an aeroplane, but because aeroplane flights are barely 20 hours or 24 hours long, it's doable. Again, at 24-hour people start to pay for luxury spaces where they have leg spaces and all that. Imagine doing that for months. And you have to understand that like for months on end, very without gravity, it's gonna be very tedious. It's gonna be like concentration camp. So you want to like you cannot pack 100 people in Starship. That is fallacy, unless you want to hurt those people or torture them. So flat out long term stay is completely different. You need big space, not only for physical reasons, for mental reasons also. So large structure flat out does not like gravity. If you see something like International Space Station or this Icarus from Martian, I think it was called Icarus, whatever have you. These puppies don't like gravity. Basically, even if you slowed it down to like absolute zero and then slowly dropped it, gravity will tear it apart. Gravity does not like this kind of awkward structure. So you have to make something big, and you have to make sure it's only in space. This is the project that NASA was originally planning to build. The whole idea is that they're not going to send astronauts to basically Mars using SLS. That's stupid. That's dangerous. They're not going to do that. What they will build something in space, and then they'll carry it to that. So this concept was utilized, and this was utilizing hot hydrogen. Basically, it had liquid hydrogen, and it used a nuclear reactor to heat that hydrogen into hot hydrogen, and it was getting specific impulse of 900, which is like 200 to 300 better than best we can even imagine. So flat out, it was a very awesome design, and they are upgrading this design itself. Only nuclear is now removed. So spinning things, and not to mention there are some concept that what if you link to BFR nose to nose with a clamp out chain and like that, and you started spinning it. You have to understand, BFR will be fully loaded with fuel, lot of fuel do not like to be spun up and down. Again, it can be done, it's just that you really don't want to be in it while it's doing that. So spacefaring is the best simple solution that you have. You can build a large structure that will allow you to have not only large living spaces, it will also allow you to have centrifuge. Now that is the primary advantages that this spacefaring will allow, that a BFR will not allow you, no matter what you do, is simply because you have space for centrifuge. Believe it or not, space has a lot of space, so you can build ludicrous structures like this. Now on top of that, once you build a centrifuge that at least, like let's say for some reason you cannot build a very big centrifuge where everything is, at least you can put bathrooms and sleeping quarters there. So that way people are quote unquote recharged with the gravity. So you can do that. That's a very awesome thing. Then it also supports inflatable modules. We have inflatable module technology right now. It has been tested in International Space Station in raw vacuum for long enough that we know for an absolute fact that it is human rated, it is human safe. We know that technology has been tested. We just have to make it bigger. Again, if you have like BFR, you do not have that much space, and it has to have maintain its profile, otherwise it will burn up in re-entry. But if you have inflatable one, you can have much larger space, and you just leave it in the space. You do not bring it through atmosphere. So that sort of option expands your what you can do. Basically, if you have 100 tons of payload capacity, ludicrously large inflatable habitats can be built, ludicrously large, and it's supposed to be reusable for at least 10 times. I'm hoping for that. 40 should be achievable. If they are reusable for that many times, you can have ludicrously, like you can have a space hotel that is going to Mars. Large solar panel is also needed because if you want to do ion engines, because if you're traveling long distance, chemical rocket is not that powerful because it will give you boost. Your acceleration period would be dramatically short. It will be like done, but your coasting speed would be much lower. So you want ion engines. Ion engines love energy. Now either you provide energy using nuclear power plant, awesome, possible, because NASA has been given clearance for kilowatt power nuclear reactor, which are rated for 1 kilowatt to 10 kilowatt, so they can put 10 of those and get serious amount of power for ion engines. That or solar panels. And radiator is very critical. Now I haven't seen any radiator design. How the heck you gonna radiate that kind of heat away, because half of the ship has half of the ship has basically heat shield, so that side you cannot have a radiator. That only gives you the other half. So, and you have to understand, like people generate a lot of heat. Our body itself is a heating element. If we are not doing anything, we are just like doing this, we are still a 100-watt heating element, and whenever doing things or exercising or things of that nature, we are producing as high as 500 watts. Now again, 500 watt is maximum, but you get the point. Like people are a heating element. How the heck you gonna get the heat away? International Space Station needs large radiator, and when I mean large, I mean it. Basically, it's the radiators, one panel is the size of a truck, 18-wheeler truck. So you get that they have multiple of those to keep it cool. So in space, basically, rather than freezing to death, you are more likely to boil to death. So you need large amount of radiator, and I haven't seen any concept of how the heck they're gonna manage the heating issue. Or they can just bleed fuel. That is also one option that will allow you to shrink the size down. This was done with Apollo computers, because they didn't want to have a cooling system, so they just had a tank of water that was slowly evaporating and cooling the system down. That can be done, but again, you want to do this for very long term. You want to have radiators. So these are the advantages that you will get building a spacefaring, rather than building something that goes from surface to surface. And this also has another advantage that is very critical and key to whole mission, is that BFR, if you have Starship, if you landed it there, you cannot refuel it very quickly unless you have ginormous amount of nuclear power. And I'm talking about like kilo power will not do anything for that. Like you need megawatt power plants. If you have that, yes, you can. You should be able to refuel it in less than what we call launch window. Basically, one launch window versus another window. Right now, current mathematics says it will not. It cannot be done in one launch window. Basically, you have to wait the second one. So you land on one, start the plant immediately. Then you at the end of basically the first one, you will have basically 60% fuel, and the moment the second one will be, you will have everything ready to go. So flat out, that fuel is a very serious thing, very serious time consuming thing. Most of your energy will be spent on just that. So having the smaller shuttle will save you on that. Basically, you have a spacecraft. Once you have built it using BFR, you can simply use Falcon 9s if you want. Basically, you can have Dragon capsule that is landing and taking off. Especially if you can design a Dragon variant that is refuelable instead of using hypergolic like a Draco does. So if you design that benefit, you do not have to this rocket that was used in the Martian movie, it was so huge because in that story they do not have a refueling capability, so it's like it basically landed with the fuel, so it's super heavy, super inefficient. If you remove the it can land on basically few tank, 50% empty tank, it will be much smaller, much lighter. You refuel it on the surface, awesome. So that is much more benefit, and that also allows you to have multiple shutters rather than having one point of failure, oh, if this goes we dead. You will have multiple 2, 3 or 4. Again, 2, 3 is a bit much, but again, if you're talking about 100 people, yes, 2, 3 is not much in those scenarios. So you will have all you have to worry about is ferrying people up there, ferrying supplies up there, and just reducing your fuel requirements. So there is benefits to that. That is one good thing about Martian craft. That is the best way to do it. Now, redundancy. Now, this is the lesson, quote unquote, that NASA learned the hard way. That you must, whenever human lives are at stake, you must have multiple points of redundancy, which they had in Apollo program, but they did not have in Space Shuttle program. Consequence: 14 astronauts went a bit up. They went a bit higher than they're supposed to go. So you have to understand this is very serious. We learned this, quote unquote, the blood way. We learned it by spending blood, that you have to have multiple points of failure. So here's the benefit. If you have this spacefaring design, if you are familiar with International Space Station, you must know that at any given moment in time there are 3 lifeboats. So if anything goes wrong, let's say a debris is imminent, it's gonna imminently strike it, people can evacuate it ISS in very quick time, and they all be safely brought down to Earth without any fuss, without any muss. They can do it very quickly. If you are on top of Mars using the Ferry design, you can do that. You can abandon ship in case of a failure or disaster or something like that. You can abandon. So when you are talking about during low Earth orbit, when you're talking about low Earth orbit of Mars, both places you have multiple points of failure. If something goes wrong, you can handle the situation. So that's awesome. Now again, you do not have the advantage doing that in while you are in transiting. That you can't do anything. That nothing. The best you can hope for is let's say a fire occurs, you can send everybody into this life pods, seal it up, and then space basically the whole craft. So you put out the fire and then hope you have enough emergency air to fill it, pressurize it back in. That can be the best case scenario. But if you are talking about everything done relying on one Starship, you have no points of failure. Basically, even one thing goes wrong, you did. And things do go wrong. That's the first thing about physics. Things go wrong. Engineering, I should say. So iron engines needs a large solar array. And if you have the Ferry, you can build a ludicrously large array. Now, high survey and relay systems that you will get, because you have such a giant thing, you will have multiple telescopes on that. While it's traveling there, it is in a very good vantage point to have quote unquote miniature Hubble plastered on top of it, so it can do multiple surveys. On top of that, once you are in basically Martian orbit, you can survey the place. You can guide the basically people on the surface, and in case of a dust storm, which will flat out damages your radio communication. Yes, dust storm will affect your radio transmission also. So you can communicate much more reliably to a very big ship rather than communicating directly to Earth. So these are the redundancy points that you can only have if you have multiple points of failure. At least on Earth, let's say you are very close to Earth, something bad happens, ship is now unlivable, everybody can be like, at least for 1 or 2 days, these things are designed to handle 1 or 2 days of passengers, so to say. So redundancy is very critical also. That's why NASA is aiming on this design rather than SpaceX design of having one thing and just going and coming back. Because right now that ship, as far as I know, it does not have a abort system. So if the booster goes YOLO, you actually go YOLO. So that is the whole aspect. That is why NASA has a multiple projects. I have provided a PDF down below that you should check it out. It has spinning habitats and all that design into it has to be used. So you have multiple points of redundancy. So this was my presentation on Space Ferry. I hope you learned from it. In that case, please click a like button. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment. Please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.